Some terminology. So we had an example on this side of a metal, something like CO. So we had sigma donation. Whenever we get that sigma donation, the proper term for that is ligand to metal sigma bonding. So they're trying to indicate which side starts with the pair and which side receives it. Now in the case of carbon monoxide, we had a pi anti-bonding orbital that looked like that. And if on the metal we have one of the dxz or dyz or one of those orbitals that has electrons in it, then we have, well, the proper name, metal to ligand pi bonding, or the very common name that we usually use, back bonding. So this is the case where the sigma bond is going ligand to metal, the pi bond is going metal to ligand. So we call it back bonding. On the other end, we had something like iodide. So that's the typical ligand to metal sigma bonding. And this time we had lone pairs, p orbitals, donating their electron density also toward the metal. And so this one, ligand to metal sigma bonding, and this one, ligand to metal pi bonding.
Would it ever be acceptable to call that ligand to metal delta bonding? Because you've got 4 lobes involved?
No, because it's not delta. This is one orbital, that's another orbital. 4 lobes would be if this had a d orbital, like an x squared minus y squared, donating all 4 lobes from one orbital. That's delta.
So because it comes from 2 separate orbitals.
This is 2 pi's. Yeah, and this also has a very uncommon name. It's just the opposite of back bonding, forward bonding. But it's rarely used. Back bonding, however, is commonly used. So I wanted to bring up one case where this makes a difference. So if you have a weak field ligand, so if the metal is in a weak field situation, high spin or low spin?
High spin.
High spin. And what kind of colors do we anticipate for weak field ligands? Which end of the spectrum?
It's going to be a short gap.
Absorber.
It's absorbance, the color that we, well, the color that we see. So the reddish end of the spectrum is where we see the weak field ligands. On the other side, we have the strong field. Ligands being the opposite. We're anticipating low spin species showing up here. And what kind of colors do we get? So they're going to be absorbing the blues. So take blue away from white light, or take green away from white light. What do you get?
Yellow.
So is this?
What?
Absorbed.
That's what's being absorbed. So what color will they look? If you take red away from white light, or if you take
That one's absorbing.
orange away from white light.
Green.
Okay, so over here, the compounds themselves are in the greens and the blues.
So this is, they're absorbing short wavelength. or they-
This is absorbing long wavelength, or sorry, high energy, short wavelengths.
Yeah,
These are absorbing low energy, long wavelengths.
so that's not the color we see. It's the
So-
color.
Yeah,
It's the rest of the color that you see. So whatever color is absorbed, it causes an electron to cross the delta O gap from the T2Gs to the EGs, and then that electron finds a different pathway, a non-radiative pathway to get back down to the T2Gs. So that delta O is the gap we're watching electrons excite over. It also explains why zinc has no color. So zinc 2, how many d electrons does it have? So if you're going to excite an electron with light, it is not crossing delta O. It's some other transition that we'd have to observe. And it happens to be in the UV. So zinc compounds all come out colorless because the delta O, what we're typically used to seeing, isn't visible. It doesn't have any transitions. Now, looking at these two colors, things that are strong field complexes that look yellow or red, weak field complexes that look green and blue, do we have any example of something that changes back and forth? Something that in one state looks green or blue, and in another state looks yellow or red?
Won't copper do
It's cobalt.
Give me an example of cobalt that does.
It's to stay the same, like 2+, not, they can go 2+, 3+.
Yeah, it stays the same. Well, changing oxidation state can cause it to happen. But there is a very famous case of cobalt changing from blue to red. And it's a simple compound that does this. You've had to keep samples dry using dry rite. What happens? Describe dry rite. I've seen it in an analytical lab.
Oh, it's
Isn't
that,
it in the
that
decibels?
blue
The
stuff?
blue.
So
Or
you
is
get
it
this,
kind of
most of the
purple?
stuff is white
Yeah.
because it's not got an indicator in it, but some of the particles are blue colored when you take them out of the bottle. It's that. Because there's no waters around, they have to form themselves in a way that they're sharing chlorides. So you get these little COCl4 clusters that are looking blue. Chlorine, a weak field ligand, gives it a blue color. And what happens when it gets wet, when it gets soaked with water?
Goes.
It turns red.
Pinkish.
Why?
Oh yeah, it goes pink.
Because you've substituted on the chlorine all these oxygens, or sorry, on the cobalt all the oxygens. The chlorine has been displaced, it now becomes a counter ion. The waters are taking up the inner sphere around cobalt. Water is a more strong field ligand, and it switches spin states. It switches from high spin to low spin, and it changes its color. So this is something that you've seen before. There's something even more intimate that you've seen before. The high spin, low spin switch.
Litmus paper?
No.
Has it-
Litmus paper, that's not an inorganic change, that's an organic one. That's not a spin state change. See it in your skin.
Melatonin? Like,
Melatonin isn't changing spin states from
no,
red to blue.
like, oh, red to blue?
Oh, blood?
Blood.
Oh.
Hemoglobin
We were thinking
relies
red
on
to
a high
blue.
spin, low spin
I was
switch.
like,
So make a
what
guess, which
changes?
one is the,
Doesn't have that.
well, what conditions does it look blue?
when it's
Non-oxygenated.
oxygenated.
Deoxygenated. So deoxygenated, it looks blue. Oxygenated, it looks red. What's oxygen doing?
Tattoo.
The oxygen attaches to the iron, and the iron is sitting inside of a porphyrin ring. And there's also some stuff down at the bottom. So sitting in the porphyrin ring without the oxygen, it looks blue. It's in a high spin state. And what happens when you bind oxygen to it? It turns red. Why? What about what aspect of oxygen caused it to switch from high spin to low spin? To go from weak field to strong field?
Our bonding has changed.
So here's my iron, surrounded by nitrogens in the porphyrin ring, and oxygen comes along with its double bond, and it's got a pair of electrons doing the metal or ligand to metal sigma bond. What else can oxygen do?
Yeah, it does.
Because it's got a double bond, it also has pi anti-bonding orbitals standing by that are empty. So iron is pushing some of its electron density back. It back bonds. So it's a thing you notice. Whenever you have a ligand with double bonds, back bonding is a real option. And it's probably a likely option, and as soon as it back bonds, anything that back bonds is a strong field ligand, and that's what causes the spin shift. So it changes spin states when the oxygen binds and the iron then back bonds. That's what causes the red color. So blood, we're looking at the high spin, low spin shift. We're looking at this very thing happening all the time.
Is the back bonding and carbon monoxide stronger?
Yes.
Is that why?
That's why carbon monoxide leaches on and hangs on a lot more than oxygen does. Oxygen is actually a pretty weak back bond because oxygen is meant to let go when you get into tissues where the free oxygen concentration is low. But carbon monoxide, azide, and cyanide. Anyone know about the poison properties of cyanide? The poison properties of azide? Yeah, you guys.
I just know they're bad.
If nothing will live in the presence of azide. Azide will kill everything because it is a massively strong back bonder. Get azide next to something, it leaches on, it hooks on to every metal that it can find, it back bonds to them, and it will never let go. So if you want to kill bacteria and fungus in your little pond out front, put azide in. Nothing will grow in it. It will kill everything.
Will it kill spores?
It'll kill, well, as soon as the spores start using metals, it'll kill the metals. It'll destroy every transition metal in a cell. Cyanide is pretty close to the same thing, only cyanide has a chance of bubbling out over time.